IT repair guide advice. And oh, you're recording. Never mind. I was going to try and restart everything and make it happen, but it worked on its own. I just need to try again. So just a quick overview of what I was talking about. Actually, I don't need to say much. I was talking about the equation sheet and listing the variables in each one if it helps you. And we're moving on to lesson 25, electromagnetic induction. So you hopefully recall that Hans Christian Ørsted happily by accident discovered that electricity flowing causes or creates a magnetic field. He noticed that a compass nearby some wires that he was demonstrating how much he could heat up the wires and basically showing how electricity works and so on, accidentally discovered that it's actually causing magnetism all the while. We refer to the branch that we've been talking about last while as electromagnetism. And that's going to start to make more sense as to why that word is used, because you can't really have one without the other, as it turns out. It just kind of seems like you can, because the magnetic field around most wires isn't very noticeable, because they cancel out the magnetic field that's going around and around a wire. You've got a north and a north to the left and a north to the right, and so on, and up and down, and all different angles, all kind of paired up. So the net magnetic field ends up being zero unless you have arrangements like coils of wires and things like that. In which case the magnetic field becomes obvious because it actually behaves like a magnet. Anyway, so he had already showed that a steady current can produce a steady magnetic field. And that's, of course, just electromagnetism. We know that that's true. There's a left-hand rule to describe directions and everything. The obvious, science often is kind of reversible, right? So I should point that out. In this case, science is not reversible. It often is. We've used that to good use, put that to good use in Lenz ray. Apparently got booted out. Recording is started. Looks like the recording still may be going. I got booted out of the meeting, but I'm back. Kayla notified me. So everyone can hear me again?
Yeah.
Awesome. Okay. So how long have I been out here? I was talking about reversibility. Okay, so reversibility in science, you already heard the idea that it's really common. For example, ray diagrams. You can reverse the direction of the rays to figure out what would happen. Ray diagrams, rays are reversible, ray directions.
Hold on, I think you need to share your screen.
There we go. The meeting started, or the recording started, but the screen did not automatically share again. Is it a Monday or something? It seems like it is. All right. So reversibility is common. For example, in ray diagrams, ray directions are reversible. Yeah, so it really wasn't much of a leap for someone to say, hey, does this happen the other way around, right? Of steady current. If steady creates a steady field, what's the obvious next question? Does steady magnetic field, I'm going to say it's specifically in the region of a conductor, cause a steady flow So, you know, and I just want you to think about that for a minute. Does that make sense? Like you just hold a magnet near a wire and then, you know, forever you've got free electricity coming from the wire. I'm hoping you recognize that that would violate the law of conservation of energy. Basically, you'd have energy coming from nothing, and so clearly that's not going to happen, right? So I think we could safely say that that's not going to happen.
Would that be like why you can't plug an extension cord into itself?
Oh, absolutely, yeah. Like if you have a power bar, you know, and you plug an extension cord and plug the power bar into itself, and expect, you know, you're not going to expect energy to keep going around forever. Yeah, you got to remember, like energy is a quantity. You know, like we're storing it, we're transferring it from one form to another, you know, and things like that. But you know, it is still it has to exist, you know, somewhere, right? So if you have a battery and you hook it up to a circuit, it has energy. It can push the electrons around and around. But if you don't have a battery, there's nothing to push the, you know, in the case of like an extension cord, the source of the energy is coming from the wall, but it's so mysterious. It's sort of just like things just magically flow, right? But the magic is physics. We know really why things are flowing. So anyways, here a magnet near a wire, sitting near a wire forever, let's say, near a wire, can't continually produce energy forever. So, you know, I'm going to put letters here. That wouldn't make any sense. A magnet just sitting there can't just produce energy forever. Like the energy has to be coming from somewhere, right? So you should be expecting this result, really, and they probably did too, because it's just, you know, clearly you can't just get energy from nothing forever. They call it like there is no free lunch, conservation of energy. You know, like it's, you know, you're not getting energy from nothing. So the reverse is not true, of course. Magnetic fields do not induce current in a wire, and I put in here this is the way it was worded where I copied this from, but I'm adding in like not continually, anyways, right? A magnet sitting near a wire isn't a source of infinite energy. That'd be amazing if it was, right? That would solve all of our energy needs, no problem. Just you want to charge your electric car overnight, just put a magnet near the front tire. You know, it'll just charge it magically. Yeah, sure. Not going to happen. Maybe on TikTok, but not in real life. 1831, Michael Faraday discovered that a moving or changing magnetic field can produce a current in a wire. So this is what really does happen. Okay, if you have a magnet that's moving near a wire, then the magnetic field near that in the region of that wire is changing, and then that does produce a current in the wire. But you have to be moving the magnet. You have to be moving the magnet, and the moving is like, you know, moving equals work equals force times distance, right? We're talking about moving, so we're talking about energy, right? We're talking about an energy transfer. So you have to be physically pushing on the magnet in order to create current. So that is called electromagnetic induction. And when I said create current, I could say induce current. To induce something means to make it happen, kind of like inducing vomiting, only not as gross, right? Back here, does a cause or induce, right? Keyword that's used there. Does it cause or induce a steady current to flow? All right, so we found that if we do change the magnetic field, right, then it induces current, only while it's changing though. So Faraday went on to develop the first generator. You know, like basically we're going to look at electric generators, how they work, the engineering design of them essentially, but the physics behind why they actually work as well. But yeah, generators use that principle. Okay. So moving on, let me know if you need this page any longer, anywhere, ever, through the whole course. Faraday's experiments, they were like this, right? So he did 3 different, basically, experiments to see what would happen. He moved a wire through the jaws of a stationary horseshoe magnet, right? So you just have a magnet and just move a wire near it. He moved a bar magnet in and out of a stationary coil of wire, and he moved a coil of wire near a stationary bar magnet. Any one of these situations, the concept of relative motion being familiar from grade 11, if you're moving relative to someone else, from your point of view, they look like they're moving relative to you. right? Like motion is relative is what we're saying. So these situations, like motion is relative, kind of kicks in here. In all of those situations, you essentially have a magnetic field that's changing in the region of the conductor. So, you know, in each of these situations, you discovered that the current was induced only when the magnetic field in the region of the conductor was changing. And that is known as the law of electromagnetic induction. So this only part in particular, right, is the part you want to pay attention to with the law of magnetic induction. Usually they say electromagnetic induction, but whatever. Close enough, I guess. Questions so far? Just pausing there for a second. Does anybody need that page more?
Yes, just a little bit more.
A teeny tiny more. Let me know when you're done, please.
Okay, I'm done.
All right, good stuff. All right, so let's just see how many ads we have to endure here. So it's just a brief little video to show what I would show if I was in 124, where you have electromagnetic induction happening. So you're going to have a magnet moved into a coil of wire, and you're going to see the meter that it's hooked up to. This is just that's actually a galvanometer. It's really, really sensitive. It can sense current flow. So basically right now it's just sitting there on its own, no current flowing, of course, right? And then watch when the magnet comes in, there's a little burst of current, and then the current stops while everything's stationary there. So the magnetic field right now isn't changing. It was changing while the magnet came in. And then what's going to happen when the magnet gets removed? Well, instead of there being a north pointing to the left and so on, there isn't going to be any more, right? So the north is like fading away, let's say, right? It's reducing. And so there's actually going to be an electric current induced then too, because you've got a change, okay? And in each case is here, it's going to do it over and over again. I want you to think about the hand pushing in is actually doing work. That's the source of the energy. And then the hand pulling the magnet away also is doing work and is the source of the energy. So you see it each time there, right? Pulse in, energy transferred to the wires, energy pulled out, or wire magnet pulled out, energy transferred to the wires. So that's electromagnetic induction. It's something you can just sit there and do all day long if you wanted, right? But the point is, you do that forever, you know, but you have to be able to supply the energy forever in order to get it to make energy forever. That is electromagnetic induction. So pictures look like that as a record in your notes. I have a flashlight in 124 that luckily I took a picture of last time I was doing this lesson. So I didn't have to drive in to take a picture of a flashlight. The current induced, you know, this is the shaker flashlight, and it has a magnet right here. You can see it. And then it has coils of wire, and the magnet flops back and forth and approaches this coil of wire and then approaches that coil of wire. When it's approaching this coil of wire, it induces a magnetic electrons to flow here. And also, while it was leaving this coil of wire, it induced electrons to flow in that one as well. So when the magnet's on its way, it's inducing current in both of these coils. And when it's on its way back, it's inducing current in both of the coils as well. Okay, so that's the law of electromagnetic induction. Put to good use in a flashlight. This flashlight has a capacitor in it, which we've talked about in previous classes. Possibly just a battery too, but more likely a capacitor, which is a very simple way of storing energy. So you just shake it, and it makes electrons flow and builds up a charge on two opposite plates. And then you've got some energy stored. You can turn the flashlight on, and you've got basically a flashlight that never goes dead. You just have to be able to shake the thing. Kind of neat. There's two different versions of it. I'll get to the other version later on as well. But yeah. So the next step for us, we're going to talk about Faraday's iron ring again. Remember, we looked at Faraday's iron ring in the past when we had. Actually, no, we haven't looked. We're going to look at it again, and I'm going to say we're going to look at it again. We've looked at it in the past, but right now we're seeing it for the first time. So this is what Faraday actually worked with, because he didn't have a good source of permanent magnets. This super strong neodymium magnet wasn't available back in the 1600s or whenever the heck he lived. So magnetism was a little bit harder to come by, and so he worked with electromagnetism instead. But he found that if he put this current on this coil, then that would, of course, make a north point in the appropriate direction based on the appropriate hand rule. And then that induces a north in this one. And then he found that while the north was building, in other words, when you first connect the current, then electric current would flow. And he would actually test to see like the resulting magnetism here, or he could have had a meter on here to test the electricity flow. But I suspect meters were a little hard to come by back then too. So he would have just looked for the needle to respond to the magnetic field that the current induced, because that was already understood. So that's Faraday's ring. And so when you close the switch, when you turn the electricity on, it induces a magnetic field to increase, basically become present. So that's changing, and so then current flows. And then when you release when you open the switch and stop the electricity from flowing, the magnetic field that was going and steady at that point goes away. And so that's, again, a changing magnetic field. And so current will flow in this coil in order to something that I'm going to tell you soon, but a current will flow, right? Because it's responding to the changing magnetic field. So that's going to go through all the details here. You notice when you close the switch, the compass needle would align momentarily, then it would go back to where it was originally because no electricity was flowing. He reasoned that a magnetic field was established in the primary coil when the switch closed. This caused the iron ring to become magnetized. That would cause an increase in the strength of magnetic fields in the secondary coil, and so current was induced. And that's how he did this. Also, when he opened the switch, as I've already talked about. So all this is on record for you here, right? So also when you open the switch, the needle would go the other way. And then do I have here Faraday's law? He reasoned that the magnetic field was reducing due to the current stopping. And so electric current was induced in the second coil, like that. Right. So that's what we said. It's all there on record for you. So the Faraday's law states that the induced voltage can be determined by. Ooh, are we doing that yet? I guess so. We're going to use this more specifically soon. This is about transformers. So Faraday's law, they talk about the idea you can actually create, what does it say though? Voltage between never turns into a coil. Case voltage stronger. Yeah, if you have more turns in the coil, you have more magnetic field, so you have more voltage induced. I'm going to stick a pin in this page for now, and we're going to come back to it anyways. Okay, so for now, don't worry about this one. This is to do with transformers, which we're going to have a whole lesson dedicated to. This is put a note there. Let me just remove that slide from the copy of this file that I'll work from in the future. But yeah, so we'll come back to that. So the easiest way to describe, so this we're getting this makes sense now. Hopefully, now we're going to look at being able to describe why the magnetic fields are induced the way they are, and also describe or predict directions. So and predict directions. So in other words, back when I was talking about Faraday's ring, if a north induces like this, right? So that's north, and then that makes there be a north here as well. Then what kind of electricity flows, right? Do the electrons go, this way, or do they go this way, right? That's what we're going to be talking about. Okay, so I'm going to just do a little screenshot of that because that's the big thing that we're going to tackle next. Lenz's law is going to help us do it in a very simple, easy way. And then we can talk about the fundamentally what's happening in terms of field lines and directions and opposites attract and likes repel stuff as well. So Lenz's law and the directions and so on. Okay, so that's what we're looking for next. So it actually, Lenz's law, just to point out right off the bat, so it's not missed, is that it's actually based on a simple, the idea of conservation of energy. Or send it back. So the reasoning of this was as follows here. Carry you through it bit by bit. So 1835, this is like way back, right? Heinrich Lenz, I always forget his first name, poor Heinrich, stated the law that now bears his name. An electric current is induced in a changing magnetic field. We know that. This current will create its own magnetic field. So think about the current that's being induced, right? Electric current is induced by a changing magnetic field. This electric current, so it's that electric current, right? Arrow pointing to it, will create its own magnetic field. Okay, so it creates a new magnetic field. Okay, we're not talking about the magnetic field that caused the first one. This is a new magnetic field. Okay, and it's because of the current that's being induced. So Lenz, Heinrich, Mr. Lenz, investigated the direction of the magnetic field and the induced magnetic field, and proposed it this way. So he reasoned that using the law of conservation of energy, he reasoned which way the direction would be. And this isn't the full law yet. This is just talking about the idea of it. Okay. Well, the law is coming up, but we're going to talk about the reasoning as well before we get there. Any questions so far? Do we need this page a little bit more? I'm not expecting you to write all these words down. All right, no one's saying anything. So Lenz's law. He imagined an apparatus he probably experimented with as well, but certainly imagined, at least anyways, that if you were bringing a north into the magnet like this, okay, so let's change that color there to be something other than red, so it doesn't look like the, so let's bring this in with a velocity here like this. Okay, so here I go. I'm gonna put like a V on there. Right, we're moving that magnet into that field like that. So he knew that moving a north end into the ring would induce current to flow in the ring. That was just like the law of electromagnetic induction, right? So that's just law of electromagnetic induction. INDUC for short, right? He reasoned some logic here about what direction it would go. Okay, so let me just get this, maybe not. Let me get this just covered up for a bit to focus us here. So he reasoned that when a magnet was moved towards the iron ring, the induced magnetic field, which is established by the current in the metal loop, could only be in one of two directions, right? Could only be to the left or the right. So basically he's saying, you know, because of this velocity coming in, we're going to end up with electrons in here. I wish this was a little bit of a lighter, different color here, but let's picture electrons like that maybe. Could go that way, or they could go this way. Really, that's the only two options. We know electricity is going to flow. We just have to try and figure out which way it's going to go. Okay, so the law of conservation of energy part of this is to do with, looks like maybe I have to send that thing to the back. There we go. So you can see the rest of the sentence. So he imagined an apparatus as shown below. When you're bringing north in, electrons could go one way or the other. So he reasoned it out. He looked at, it's like if electrons are going the first way I have drawn, which way would the magnetic field be? A little pop quiz question for us that doesn't count for anything other than pride. What direction would the north be, left or right? If electrons are flowing the way I'm showing here in with the right beside the coil. Curl your fingers in the direction that electrons are going in the circle. So you have your hand facing towards you, hopefully, with your fingers curling towards you, right? Your thumb's pointing to the left, right? So that would create a north that would be sticking to the left, or electrons would go the other way, which case you flip your hand around, have your fingers curling like away from you, your thumb automatically points to the right. Okay, what would happen if a north was created this way, right, or this way? Think about what would happen. What would happen to the magnet that's coming into the field if a north was created this way? So this is north created here. What would that do to the magnet when you're trying to bring it in? And versus what would happen down here? Let's focus on this one actually first. If a north was made that way, then we have this the magnet coming in that is like this, south and north. And then we'd have the south of that end of that north being created here. What happens right here? Opposites do what with magnetism?
Repel, so like would they flip
Attract.
around?
So the first one would repel, right? This one would actually attract. The opposites attract, right? And so this would cause an attraction. So basically he said, okay, we take a magnet and we bring it near a coil of wire. If the magnetic field made by the electricity that's going to be induced caused the magnet you're bringing in to attract even more to the coil, then that's going to be like a spiral. It's going to be like a snowball effect. You're going to bring the magnet near the coil of wire, and then it's going to make a magnetic field that's going to pull it even closer, which is going to make even more magnetic field, which is going to pull it even closer, which, you know, it's just going to be, it's going to spiral out of control, and you're going to be getting like huge, infinite amounts of energy out of this thing that you can't control, which is ridiculous. That's not what's happening. We're pushing on the system, transferring energy to it. It's not producing energy, right? It's not the source of the energy in the first place, I should say, right? So basically, he realized that if the field were to the right, then the magnetic field would be accelerated. That's this option here, right? That happened conveniently is right beside this, right? So it would be accelerated by the magnetic field created by its own movement. This would lead to more and more magnetic field and more movement, resulting in more and more energy being released, right? Since this would require energy to be released, which had no source, the magnetic field can't do that. And so it must be in the opposite direction, so that the induced magnetic field opposes the magnetic field that created it. Okay, so since this would require energy without a source, the can't happen. And so the it's gonna be a long sentence here, magnetic field can't, the current can't, yeah, and so can't be induced in this direction. And so, you know, there's another and so coming up here, but therefore maybe the magnetic field must be in the opposite direction to the field that was causing it. I'm not sure if I'm happy with that sentence over. I got to reread it. Since this would require energy which had no source, this can't happen. And so current can't, I'm going to put it just in brackets to make it. So current can't go in that direction. Basically, therefore, the magnetic field must be in the opposite direction so that the induced magnetic field opposes. And I'm just going to add on here, current must be induced electron. I'm going to say electrons flow because I am picturing electrons there. Be induced in the direction shown above. The top of the page, this one. If the electrons are induced that way to flow, then that would make a north that opposes it, which is much more realistic. It's going to oppose that motion, and you're transferring work to energy to it as you do that work. Just like energy pushing electrons through a light bulb, right? As the electrons' energy is taken, it's hard for the electrons to go through the light bulb. That's why it's transferring energy to the light bulb. So we're not totally done here. Obviously, we're going to say there's a law, right? So anybody need that page a little bit more, though? Or are we just kind of talking about ideas here first anyways, right? But no one is saying. So Lenz's law. I feel bad because you must have to be on the ready to click your mic, right? But just have your mouse ready on the ready, I guess, for where the button is. Lenz's law basically says when the magnetic field in the region of a conductor changes, electron flow or current is induced so that the magnetic field caused by the induced electron flow or current opposes the magnetic field change that caused the flow, caused the induction. So the key there, the emphasized opposes with the big red underline, right? That your magnetic field is going to oppose that. So what we do now, let's just jump to a question here first, or like an example here. But if I'm bringing in a north like that, basically what you do by Lenz's law is you say, okay, I know that there is going to be, let me just do this way with my mouse here. But we know that there is going to be a north that is induced this way. Okay, so this north induced this way, we know that what's going to happen by Lenz's law. So that is the magnetic field induced. And of course, the direction is by Lenz's law. So let's say maybe direction of magnetic field induced by Lenz's law. Okay, so that is important to recognize. So then you look at the electron, or the current actually here. So right-hand rule this time, current moving in the direction of the yellow there. You can see your thumb, if you curl your fingers in the direction of the yellow, your thumb's automatically going to point to the left. And that opposes that north that's coming in. Okay, so maybe I'll just move this down because I do want to talk about the actual field lines as well, because you can actually explain this based on field lines. Just Lenz's law is just so much easier. Okay, so we looked at field lines with between two current carrying conductors, and we saw like if this wire had electrons flowing out of the page and this wire had electrons flowing into the page, we said, oh, there's going to be a magnetic field, electrons going out of the page. I'm just using my left-hand rule to get the direction here, like that. And then into the page is going to be like that. And so we reasoned out that there's going to be a repulsion. We have likes repel, likes repel. Remember, I'm just reminding you that we've done that. So recall, right? So in this case here, if we have electrons going into the, or current going into the page, thumbs pointing into the page of your right hand, your fingers curl in the direction of this top loop. And at the bottom, your fingers would curl in the direction of this loop. And so you can see there's a big old north pointing that way, right? And so that north here is where we could talk about likes repel, just like this, right in here. So we've got the red from the magnetic field direction, and we've got the blue from the magnetic field induced direction. We've got likes repel. So the reasoning about why they have to repel is still very sound, right? The idea of conservation of energy. Lenz's law just allows us to claim the direction without having analyzed, the idea of likes repelling, what direction the electric field or magnetic field induced would be. Okay. So in this case here, we've got a north that's going away. If there's a north going away, then there's going to be a big there's going to be a magnetic field induced like this, because then that's going to make a south right here. And that south is going to make it, it's going to oppose that change. When you play around with this stuff, if you move a magnet near a coil of wire, you can actually feel it physically dragging, causing it be hard to move the magnet. Okay, this is one of those ones that would be super nice if we could be in 124 to be able to play with magnets near metal and see that it really does cause it to drag. It's like you're dragging it through a really dense liquid or something. It's like hard to move it. Okay, so it's electromagnetic resistance. It resists the flow, resists the movement. Okay, so the opposing magnetic fields induced really resist movement. So the magnet movement, you can feel it. Okay, so unfortunately, I can't demo that for you right now, but it does really work. All right. Always let me know if you need something. For example, I need to reset my screen. Looks like it's working now. So determine the direction of the induced magnetic field for each apparatus shown. So in this, we've got a coil of wire obviously here, and we are going to be moving the magnet to the right. So what direction is the magnetic field induced here in order to, well, what would happen based on Lenz's law? If the magnet's moving to the right, then picture we've got a north that's leaving, right? So this north is leaving. We want to oppose that. So we're going to induce what kind of magnetic field right here. In order to oppose that, we're going to induce a south, because the south would attract the north and make it hard to move the magnet away. You'll actually feel it being dragged, like a drag force on it when you're trying to move it away. And so it's going to look like that, right? The electricity is going to flow in the coil so that a south points to the left. Okay, so then this attracts it and tries to stop it from going away. So the induced magnetic field would work to oppose the motion of the magnet, so that it would be pointed to the left. So there's a south and a north, and we've got an attraction situation. So that we have attraction, and so give me a second here. We have attraction. I do not like my computer. Attraction, which it's a drag force on it, right? I'm going to say felt. Right? There's a drag force felt as you're trying to drag it away. You could even actually analyze out which way electron or electron flow or current would be. So if you want a magnetic field to the left, if you're going to look for current, you're going to use your right hand. So you're going to be like, oh, so the current must be this way. I just have to use your hands and use your hand rule and picture that current would be this way, right? Or obviously your left hand would predict the exact opposite direction for electron flow. E flow would be this way. So let me just redo that with a different color, or stick an or on there with a different color this time because I tried. There we go. Or we'd have electron flow. So remember that by definition, electron flow one way is the same as imaginary, traditional, ridiculous current the other way. Another one to try here. What about this case? What if we're bringing a south in like that? What kind of magnetic field is going to be induced right here in order to oppose that south that's coming in? We'd have to want to repel. So we're actually going to have a south here again, aren't we? Right? So we're actually going to have a south there again in order to repel that south that's coming in. And so again, the magnetic field induced would repel the south, so it would be pointed to the left, i.e. we're going to have a south right here. When they say pointed to the left, they're meaning that the north pointing end is here, but I'm focused for sure more on the idea of the south and the south repels, right? So let's go here, south and south, purple here. Trying to get the purple. You see my clicking on it, right? So the south induced repels the south coming in, right? And again, there'd be a resistance felt. That is Lenz's law. So lots of different ones here. I'll leave that one for you, but this one here, oh, they're saying which way is the magnet moving? So is this arrow in here behind door number whatever here, is that arrow pointing like that, or is it pointing like that? The left or the right? So if you have a magnetic field like that, then that means that this is actually a south right here, which means it's trying to repel, which means it must be coming in, right? So the motion of that magnet must be in. Same wording. Okay, so hopefully you're getting an idea of the hang of using Lenz's law to predict things with electromagnetic induction. Right? Any questions at this point? All right.
Sorry, I'm not really sure where like the arrow comes from if they're repelling. So like, what does it represent again?
So remember this arrow here, the black one, represented velocity, right? So I tried to use black here, but it never likes to select the thing until I'm really forceful. So we have a magnet moving in, right? And so I was able to figure that out because I could tell, they told me the magnetic field direction, right? So if this is a north over here, this is what they're telling us, right? Then that implies that there's a south here. And so that means that the magnetic field induced was so that it would try to prevent the south from coming in, right? Because so that means the south must be coming in order for it to want to induce the south to oppose that motion. If the magnetic field was the other way, right? So that was induced, then we'd be able to say, oh, what must have been happening then for this case, right? If a north is there, and we want, So if a north is here and we see there's a south, right? We can tell that's an attraction. And so we're saying, oh, so that induced field was trying to attract the magnet. In other words, it was trying to stop it from leaving town, right? It was opposing the motion. So if they had have shown us a magnetic field the other way, then you'd say, oh, that must have been caused by a magnet moving to the right. I was going to get a magnetic field that opposes. And you just have to get good at recognizing south, and south means repel, right? So repel. It's repelling. It's trying to stop movement inward. So therefore, it's this one here. Does that help a little bit?
Yes, it does. Thank you.
Perfect. All right. So another example of using Lenz's law. This is where we actually apply our knowledge and be able to figure out generators. So this line here about how how Faraday went on to use this to create generators. All he really would have done at that point in time is realize that an electric motor can operate as a generator, and I'll show you why. Okay. So this is an electric motor being physically manually turned, and we're looking for the result of what that would cause. So the conclusion is going to be, spoiler alert here, that it's going to generate a flow of electrons by electromagnetic induction. So this is a generator, a motor that you're physically turning yourself, creates electricity. So it's again another example of reversibility of science. With a motor, you put voltage on it, it makes movement. What happens if you go the other way around? If you move the thing, well, it creates the voltage. So it's as a motor, let's put this here. As a motor, voltage leads to movement. So this is voltage like joules per coulomb business, right? So let me draw that better, because V could be velocity. So with a motor, we know voltage, volts, leads to movement. I'm going to shrink that down in a second. The opposite, right, of this, movement leading to volts, is when it's a generator. So I honestly, the only example I can think of where the reversibility of science isn't true, the only one off the top of my head where the reversibility of science isn't true, is with the electromagnetic induction. It's so many times in my teaching, I'm able to say, hey, look, and this is just reversibility. It makes sense if it works A to B, then it's going to work B to A. You know, it's obviously in chemical reactions, things like that, if energy is released, you'd have to sort of gather up that energy and whatever, but that's exactly what you can do, right? You can force water to get extra oxygen atoms added to it and force it to become hydrogen peroxide, right? That's the reverse process of hydrogen peroxide. We're releasing oxygen as an energy, that as a reaction that releases energy. Like reversibility of almost everything is very logical, not necessarily possible, but very logical. Anyways, I've got this magnet moving. Okay, so I'm going to physically rotate this thing. I'm going to force it myself to rotate. What magnetic field will be induced here? Think of what's happening. We have a coil of wire moving in a magnetic field, and so there's going to be electric flow or current induced, right? Electron flowing or reverse direction for imaginary positives moving. But I'm pretty sure the positives are locked into the copper of the wire, right? So they're not actually moving. So let's talk about electron flow. Okay, so what kind of magnetic field will be induced on this end right here, right? What kind of magnetic field will be induced there to try and prevent this movement? North or south? Anybody? Hint, it's going to want to attract to the north here, right? So this right here, we're going to want to have attraction right here. So this one needs to be attraction to resist the movement. Don't be shy. Is it a north or a south? Obviously, it's going to be
South.
Yes, thank you. Obviously, it's going to have to be a south there in order to attract to resist that motion, right? So if that needs to be a south, then that means that the magnetic field itself, the way we draw it, is this way, right? The north's like that and the matching south on the other end. So now we can use our left-hand rule for electrons and say my thumb's pointing that way, which means my fingers curl around naturally this way. My electron flow would be like this, all the way along through all these coils. That would be E flow, right? In there. So then now we have to look at the way this thing's drawn three-dimensionally here. We've got electrons flowing around and around and so on. Looks like the electrons are going to go around this way now. Sorry, they go around here, around and up, and then in up here, right? So I've got electrons flowing this way, which means electrons are going to hit this commutator, hit this brush, and go out this way. So this thing's going to generate electron flow in the wire like this, all the way around through that circuit. And so if you had an ammeter here, it's going to read current. It's going to read movement of charges, right? Still drives me crazy that current's technically positives, but hopefully you're over it. So yeah, there's a magnetic field changing due to relative motion in the, the coil's in a magnetic field. And so the electron flow is going to be induced so that a magnetic field tries to stop the movement. In other words, it's going to have to be a south. Probably says. Yeah, electron flow induced, resulting in magnetic field that opposes the motion. Okay, so that's a generator. Just using a motor and forcing it to go. If we look at this situation and we analyze it further as we go, let's just clone this page here. Okay, if I have this guy here, I'm gonna have to erase some of my drawings there. It's gonna get messy in a second. But as I continue to go here, see how it's still in the middle here. Watch this wire connected to the commutator. It's still connected, right? So a south was opposing things. What opposes things now? If I'm still trying to move towards this side here, right? I'm still trying to move like this and get to the south. See how it's going to be a south again? So a south still is going to, again, oppose motion. So south still opposes motion. So we still have the south, so we still have the same electron flow, and we're still connected to the same electrode, so we're still getting electron flow the same way. What happens next is pretty genius, because this commutator, let me just undo that. That wasn't so genius. Just my computer being a jerk. Gain control of my mouse again here. All right, undo. There we go, perfect. So as I turn here now, see the genius thing is that now the wires aren't connected anymore, and the thing just continues to spin because of inertia. And now the wires are connected the opposite way. And so now we've got the thing flipped 180 degrees. So clearly the wires are oriented the opposite way, but so is the way they're connected. And so now a south making the same electron flow makes electricity go the same way. this thing will produce DC current. Right? Because of the way the wires change direction, but then so does where they're connected to, and so does the coil flips, and so it produces direct current. It's always going to go the same way. Right? So that thing produces DC current. If we have, I was supposed to analyze that on these pages here, but do you follow me? What I said there? Yeah. So an example of a generator like this. This little flashlight here, you might have a lot of people have these. They're from Costco, and a lot of people shop there. They have a little crank on the back, and you turn it. What you're doing is you're forcing a motor to turn. Right. So if you took this thing apart and took a battery and applied it to the wires, it would actually make that crank, that handle, spin. It would operate like a motor. Okay. I wanted to talk about a split ring commutator. Good. Where's my file? Doesn't matter. I'll just, I forget where we turned. I had a page. Oh yeah, with a solid commutator with two rings, one above the other. So instead of having this split, like you've seen in the past, I can probably Google it for you. AC motor or AC generator armature. Should be able to get a picture of that pretty easily. AC motor armature. If they're going to show it well or not here. Let's see. This one actually does show it, but it's not a real one. But basically, instead of having a split ring where it's half and half, they've got two rings. They have two slip rings, basically. And so you're always contacting this one, and you're always contacting this one. Okay? So instead of having it split where it's half and half, instead it's two separate rings. And they're usually just one after the other on the shaft that you're seeing in these diagrams. So what does that do? So what that does is, by the same logic as before, as this thing is moving this way, we know we're going to get a south, and so we know we're going to get electron flow, right? Which means we're going to get electron flow going this way, right? But then what happens is when we flip around to, here, this end that we followed along to here, this end near here has to become a north now. Right? It's going to be a north to oppose this motion by Lenz's law. So now you're going to want to get electrons going the other way, right? So this means electron flow has to switch. E flow switches direction, which is true in the last one too. We're still saying the same thing here, like it still has to switch direction, so that has to be a north. But the problem is, or the difference is now, is that the wires continually connect to the same side of the coil. Okay, so the wires are still connected to the same side of the coil, and so that means the electricity switches directions. So I was anticipating finding a picture where there's a shaft of an armature business here, and this one, the split ring one that we already talked about, has like a two halves like this, right? And so the wire actually switches from one side of the coil to the other. With a slip ring commutator instead of a slip ring and split ring, very similar, right? But you'd have a coil, or you'd have a ring here, and then another ring here, right? And so you're contacting, to the same parts of the coil all the time, same end of the coil wires, and then because the coil flips around, that reverses the direction. So anyways, that would produce AC, and that's important because we're going to learn tomorrow that AC is very important. So electron flow switches directions. We're talking about AC current. Spoiler alert with tomorrow's lesson, AC is important because we need changing magnetic fields, right? So changing magnetic fields, because that's what causes other magnetic fields to change as well, right? So that's just changing magnetic fields. And so, you know, that is a happy face right there. Changing magnetic fields, that's going to be useful. Because then when you have a Faraday's ring, wherever that was along here, Faraday's ring, yeah, there we go. So if this guy is going back and forth on its own, this one's going to continually induce an opposing magnetic field on its own as well. Okay, you don't have to switch this thing on and off in order to get pulses of energy. You're automatically going to get pulses of energy all day long, as long as you're continually pulsing energy on the other end, which is what AC does. So that is possibly going to be included in a little bit of the questions tonight, but certainly more focused tomorrow. Questions? All right. So a neat Lenz's law demo is when you drop something that's not magnetic into a copper tube, which is a good conductor, but it doesn't attract magnets. It doesn't get, the magnet doesn't get stuck to it. So if you drop like a rock or a bolt or whatever through, it just drops like you'd expect. If you drop a magnet through, then what you have here, let's analyze based on Lenz's law. We've got a north magnetic field building in this region, right? We've got a north building in this region. So electrons are going to flow. So they're either going to flow, electrons are either going to flow this way or they're going to flow this way, right? Either way, they're going to go around and around in the loop, right? Electrons are going to be induced to flow. And we can actually sort of predict which that they're going to flow in a circle, first of all, but also which way they're going to go using Lenz's law. Do we want, is it going to be a north or a south that gets induced here? So is this a south or a north in order to oppose the north that's coming in? Anybody want to cue their mic? In order to oppose this north that's coming in, we're going to have a, no?
Another north.
Another north. Thank you very much, right? So it opposes the motion, right? So if that has to be a north, then you can say, oh, well, using your left-hand rule, in order to have a north pointing up, coincidentally, I have this in the right direction here. That wasn't actually planned out, but this is the direction electron flow would have to be in order to make a north point up. When a north points up, it opposes the magnet as it drops in. Okay, so let's follow my wording here. There's a change in the magnetic field in the region of the tube because of the north coming in. So there's going to be a current induced such that the magnetic field produced by the induced current opposes the change. A loaded paragraph, right? But we need to oppose that change, which is this little arrow going up right here, right? So in other words, it's going to say here, you need to have a north pointing up to oppose the north coming in. Okay.
Mr. Horn, can you explain again like how the hand rule works, like how you got that the direction of the electrons there?
So it started with us saying that we knew we had to have a north up. So I'm going to start by drawing my thumb with a north pointing up. Okay, that's my fingernail and my thumb there. Okay, and so that's a thumb. And then now my fingers naturally of my left hand would curl this direction. Okay, so that finger curl direction is your electron flow direction in order to have a north pointing up. And I'll put my fingernails on there too. Follow me?
Yeah.
Good. So we knew this had to be true, right? Therefore, let's go blue here. We know this is needed. So let's say this is needed to oppose this, this north coming in, right? And so, yeah, we have to therefore have electron flow in that direction. Satisfied? Yes?
Yeah, that makes more sense. Thanks.
Good. Oh, check that out. I just didn't show it yet. The diagram that that I was drawing. But I did at least show that, you know, you can even draw these yourself to help yourself in explanations and so on. So that's, I don't mind that I drew it as well. Yeah, so that's the north direction and we're good to go. So this is a demonstration with a copper pipe and a magnet, just like I would show if I was in room 124. So we're not missing out on a huge amount, except you can't feel it. I wish you could feel the magnet. Feeling the opposition to the force is neat, but you can certainly see the result of this. So we've got a copper pipe and we've got an object going to be just dropped through shortly here. So this is just an iron ball, just a marble basically being dropped through. And he's going to put his hand down there and he's going to catch it. It's like boom, just lands right away. I don't know if you can see it or not, but it took like 0.02 seconds to go through the tube. Okay. Then he takes a magnet that's the same size, same weight, same mass. Not that that would matter because all objects accelerate at the same rate due to gravity, right? But if this thing doesn't drop through just as quickly, then the explanation, of course, matches what we've said about Lenz's law. It's going to, the magnetic field induced or created by the current that's induced in here, because of that changing magnetic field, the north coming in is going to make a north go up, going to induce a north up. And so the electrons flow in the correct way to make that happen. But really we're focusing on there's a north opposing it, which is going to slow it down. So let's see how slow it goes. It's released, and then boom, there it goes later on. Isn't that crazy? It takes about 4 seconds for it to go. It took 0.02 seconds before. So 4 seconds divided by 0.02 seconds. It's a factor of 200. It's slowing it down by. Like, it's crazy how slow this is. The first time I played with this little Lenz's law, Lenz's tube apparatus, I was quite shocked how much it slowed it down. I wasn't anticipating it taking like a good 4 seconds for it to go through a tube. Okay, it's a huge effect. This is the apparatus that I have in the classroom, exactly, and it's exactly what you'd expect. They have other ones where there's a cut in it, and then it's not as much of a slowdown because the current can't do its thing. So this one has a cut in it. So let's add this in. If the electrons can't flow, so this one has the tube is cut. Therefore, electrons can't flow. Right? They can't do their thing, right? They can't do this as easily, as much at all, if at all. And so the resulting, it leads to way less force. Let's say, well, yeah, let's just say there's no opposing magnetic field created or induced. I didn't actually notice that this one has a slice in it, but that is what would happen. If you have the slice, then you can't have electrons flowing, and you don't get you don't get a repulsion force. You don't get that opposing force, which is neat. So this is another one that has some other video clips to do with this. Switch your bicycle to electric. This is a switch bike.
This is a switch bike. No.
Whatever. All right. So a bunch of different demos to do with this coming up here. And maybe some explanations.
We've got 2 magnets here, and we're discovering, not surprisingly, that opposite poles attract.
Kind of neat. He's got a magnet that's strong and able to rotate, and so he's just turning this one, and this one responds. And that actually helps you sort of picture like the magnetic field as well, right? There's a magnetic field around this one because it's causing forces on this. This is the appropriate object, quote unquote, right? The appropriate object in the field. You can tell there's a field if there's a force, and clearly there's forces between them.
The red pole is north, and the unmarked pole is south. According to Faraday, when a conductor is pulled across magnetic field lines, an electric current flows in the conductor. Now, we already know that a current in a conductor will in turn create an...
So that's just Faraday's, right? When you have a changing magnetic field in a conductor, electrons are going to flow in the conductor. Lenz then put a direction to it afterwards.
Another magnetic field. And the important point, and this is a really critical point, and it's why Lenz's law is so important, the magnetism that's created in the ring fights the change in magnetism that produced it. So in other words, when I try to push this magnet through the ring...
Isn't that an awesome diagram? Like picturing all of these magnetic fields around this wire. Right here, you've got a bunch of norths that point to the right, and those north pointing to the right, the way they have it shown there looks like that. Or am I misinterpreting? Oh no, they're to the left. I was just following this one right here. Is to the left. Good, because then the left pointing repels the north that's coming in.
The ring creates a magnetism that pushes back. So I don't.
Oh, you know what? They're talking about current.
I don't get an electric current without working. Let's set up a demonstration.
There's a strong
Take
looking
the
horseshoe
aluminum
magnet.
ring we started with. It's light and it's not magnetic. We'll drop the ring between the poles of a very strong horseshoe magnet. If there were no magnetism here, the ring would fall under the influence of gravity. But as it enters the poles, we induce a current in the ring because we're increasing.
And that, you see it slow down there when it's going through. If you were holding the ring and trying to just move it up and down, you'd feel it resisting the motion that you're trying to apply on it.
Magnetic field lines, or what we call magnetic flux, enclosed within the ring. A current starts flowing in the ring becomes an electromagnet. The poles of the induced electromagnet oppose the poles of the horseshoe magnet. And so the magnetic field of the big magnet creates a net upward force on the ring, opposing the force of gravity and slowing the ring's descent. As the ring exits the pole region, the flux that it encloses starts to decrease, inducing a current in the opposite direction. But that current also opposes its fall. In each case, the ring falls much slower than we expect it to. This is
so, long story short, what he was saying, when you're coming in, then magnetic fields are building, and so the current induced creates a magnetic field that opposes that change. And then on its way out, the magnetic field of this giant horseshoe magnet is reducing. And so current's going to be induced in the opposite direction, making a magnetic field that actually attracts to that and tries to slow it down. So you're repelling to slow it down, then you're attracting to slow it down.
Lenz's law applies. One of the critical tests of a scientific theory is whether we can predict anything. If what we've just said about Lenz's law is true, if we can keep current from flowing in the ring, the effect disappears. So what if we were to take the ring that we just dropped and put a small cut in it so there was not a closed path for current? According to that, the ring should not be influenced by Lenz's law, and it should drop entirely under the influence of gravity. Here we've got a ring with that cut in it. When we drop it through the magnet, we note that it falls unimpeded with no surprising delays, as we just saw in the previous example.
Because the electrons
Another way
can't
to have a
flow.
look at Lenz's law.
So that is
would be
the same as the one where I showed you. I don't have one of these in 124, but the tube with the slice, electrons can't flow, so there's no opposing force. So he showed a different version of that there. Let's go back to it.
That instead of one ring, as we've just seen, we had many rings. Those rings were stacked together to form a tube. If a magnet were to go down that tube, it would induce a current in each ring, and each current would fight back against the magnet. So we'll take a thin tube and
so he's getting you to imagine that a long conducting tube is essentially a whole bunch of rings, right?
So we'll take a thin tube
all lined up.
And a powerful magnet. The tube, of course, would be not made out of iron or steel, so that there were not any magnetic effects on the tube. Let's drop a pencil through the tube, a non-magnetic object, to see that under normal circumstances, gravity controls the behavior. The pencil falls through as rapidly as we expect. But when we drop a magnet through it, it takes much longer. Why is that? As the magnet falls through the tube, the obvious force acting on it is gravity. But along with gravity, as it falls through each ring of the tube, it induces a current around.
I like that they're showing the current induced in the opposite directions in each end. So this is current inducing a pole so that it attracts to this to try and slow it down from dropping. This one's making current so that it produces a north up, repelling the fact that it's coming in. So actually get current induced in opposite directions on either end of the magnet, which is interesting.
Ring. The current produces a magnetic field that pushes back on the magnet. So the magnet's now feeling three forces.
He didn't explain that
One
very well there,
downward
did he?
on
The
the magnet.
push is back on the magnet business. It's actually attracting here to slow it down and repelling here to push it up. Both of those forces are directed up to try and stop it from falling.
So the magnet's now feeling three forces. One downward from gravity, one upward as the lower
There he
electromagnet
goes.
repels it,
Explaining it better now. It's good.
and one upward as the upper electromagnet attracts it. The
So in
two
that case
magnetic-
there at the top, so yeah, this is pointing a north down, and we know it's a south of the magnet, so that's an attraction. And then again here, north up and north down, you got two norths. So it's repelling.
forces counteract the gravity. And so the magnet falls at a constant velocity instead of accelerating like a freely falling body. So why does Lenz's law matter? Well, it matters because it tells us we can't get something for nothing.
So it gets to constant velocity as it sort of balances between, like if it slows down too much, then the magnetic fields that are repelling it dissipate, they go away, and so it starts to accelerate more, and then it, it creates more magnetic fields that oppose it, and so it travels with constant velocity as a result. It just balancing back and forth between too much current and too little current. It balances out really quickly.
That when we make electricity, we make it by fighting magnetic fields, by pushing, so that we still need mechanical energy to make electrical energy. Energy is conserved even if we switch forms from mechanical to electrical. We can see Lenz's law come into play in many places. One of the more interesting places is in the behavior we call maglev, or magnetic levitation. Magnetic levitation generally applies to an object moving over a long distance of a non-magnetic conducting material. We can't set up a long track like that fits in our laboratory, but if we take a stationary magnet and a spinning aluminum disc, we can get the same effect. We have a spinning aluminum disc underneath a strong rare earth button magnet. As the disc spins, we'll hear the noise of the magnet scraping along the aluminum disc. And as the aluminum disc picks up speed, the rate at which the magnetism changes for each surface area point of the aluminum gets higher and higher. That induces more current, and more current produces more magnetism. If we move fast enough,
So again, relative motion, right? Instead of having a magnet moving along, changing a magnetic field in the region of a conductor, instead you got the conductor moving in the region of the magnetic field. And so as the aluminum comes in, it's going to have current induced in it that makes a field to oppose the change here. And then as it goes away, it's going to make a field to oppose the change. So it's going to make a north repelling a north, let's say, and then a south repelling a south. So there's little currents getting induced in the aluminum that cause the repulsion to lift that magnet off the track if it was a long track. Kind of neat.
the induced magnetism pushes back on the button magnet with its own weight, and it lifts the magnet off the surface of the aluminum. We've now seen 3 demonstrations of Lenz. In all of them, we have discovered that if we produce electric energy, we've got to do so by putting in mechanical energy.
So he keeps coming back to that idea that, you just can't just stick a magnet near a wire and think that it's going to produce energy forever. You have to actually do work on the magnet to get work out of the electricity.
That the laws of physics that we've learned in mechanics transfer right over to electricity and magnetism. That forces come in pairs, that energy is conserved, and that these electrical behaviors that are not as intuitive as the mechanical behaviors still follow all the rules.
So that's good stuff. Another example coming up here. This is the one where you can really feel it. So this is an engineering application of this. So a Pasco cart with a big sheet of aluminum sort of stuck in it, 2 magnets. And what happens is, as this thing comes along, magnetic fields are obviously brought in and change in the direction of this. And so on the front one side, let's say this disc is like a north on one end and a south on the other. So it's a north and a south on the other end. Then as this region comes in towards it, it's going to induce a north here. Actually, sorry, it's going to induce a south here to oppose the south. And then as it leaves, it's going to impose a north here to go away. And so you're getting little currents, little electron flows in here to make that happen, right? So you get a lot of electron. I'm just going to show like with a circle, like electron flow to make the norths and the souths. I'm not worried about the direct. I'm not bothering to think through all the directions there. You know there's electrons flowing in the aluminum in order to cause norths and souths, to repel and attract, basically to slow this thing down. So you slide the current towards this, and it literally goes along with 2 meters per second velocity, and it goes right down to a stop very quickly. Actually, it's crazy. And if you just take the aluminum and try to move it with your hand in the middle, you feel the resistance. This is the brakes they use on rides like this at Canada's Wonderland are actually exactly like this, because they don't want brake failure, like, ooh, the hydraulic fluid in the brake pads didn't, and then people die. This will never not work. And so they have a magnetic braking that slows you down to a non-paralyzing speed, and then actual brakes kick in afterwards. Actual meaning like friction brakes, where they have brake pads and so on, kick in to slow you down the last little bit. But if the mechanically applied brakes ever did fail, you would just hit the ground with a thud, but not enough that anybody would be injured. The magnetic braking always will work. You've got permanent magnets, you've got conductors. It's a no-fail system, which is pretty awesome. Regenerative braking, electric vehicles, it's now really common, but any kind of electric vehicle that has motors that turn the wheels, if instead you make the wheels turn the motors, they're going to generate electricity. So you don't have to have separate components in an electric car to have regenerative braking. You just have to have control mechanisms to say, like, okay, you know what, we're going to use the energy from the coil, and it automatically slows it down, which is pretty cool. So that's regenerative braking circuits in cars, of course. Electric motors, when run in one direction, they convert electrical energy to mechanical energy. The other way around, if you're using the mechanical energy of the rolling, it produces energy, right? So it actually charges the battery while you're slowing down. I will just show briefly here the idea of the generator effect analyzed fully, rather than Lenz's law. But Lenz's law is pretty sweet, obviously. So we normally would just use Lenz's law. But in this scenario, I think maybe Lenz's law isn't as easy. It's really good for you to recognize the significance of this. Okay, so you've got a wire that's being moved up in a magnetic field. Any questions? Do I need to pause for a second? These are just ideas, like applications, right? All right, no one's keyed their mic and said, hey, slow down for a second. Yeah, if we have a wire, the key to recognize here is that we have electrons in a wire. And so if we're moving the wire is equal to electron flow. Okay, so moving the wire is equal to electron flow. Right, it's equal to current in the imaginary world of positive charges flowing, right? So moving the wire is electron flow. And so if we analyze this out, we've got electrons flowing up, thumb pointing up, please, in front of you, left hand thumb, stay pointing up, thumbs up, everybody, and then extend your fingers so that they go from north to south, direction of this blue arrow here. What direction is the palm of your hand facing now? Palm of your hand is now facing towards you, right? And so that's actually going to induce electron flow this way. Okay, electron flow would go that way. And so you actually have electrons flowing through the wire because of moving the wire up. Okay. If we were to look at the Lenz's law version, I guess it would have been on the way in, you want a magnetic field this way, right? In order to oppose the magnetic field that's already there, right? So picture a magnetic field like this from north to south, and then you're bringing a wire in, right? Well, you want that wire to have a magnetic field exactly like that, so you get opposition, right? And so then that's like, okay, well, the left-hand rule would work in the other way around, where you'd say, oh, electrons would be flowing towards you, so that when you move it it's going to oppose, right? We can talk about even what happens once the wire goes through and is on its way out the other side. So it's on the way in. On the way in, it has this, and then on the way out, you've got that north-south, the magnet. I'm talking like right here, right, north to south. So we've got the north-south direction of the field, magnetic field, and now we've got the wire moving up, right? We're going to want to have, in this case, the opposite magnetic field, right? So if we have an opposite magnetic field, a south and a north, like that, then we've got attraction, right? So we've got repulsion on the way in and attraction on the way out. Either way, it's resisting the flow, or the movement of the wire, I should say, which is really electron flow. So more than one way to analyze this thing, I suppose, right? But either way, we end up with the correct answer. We get electrons flowing, and it's actually really nice to visualize here. This is the hand rule, thumbs pointed up, fingers in the direction, and so on. The electrons literally have a push on them from the magnetic field, right? That's electromagnetic force on them. So this force here that we're showing here, the push out of the page, let's go purple, it's more emphatic here, right? That's a force on the electrons. What makes electrons move, what makes electrons have a force, really we're talking about, this is EMF, electromotive force, right? So we're literally saying, okay, we've got a force on the electrons causing them to go out of the page because of the left-hand rule. We've got a magnetic field, we've got electrons moving. So we're saying it's a force, it's going to make the electrons go. And I'm hoping now you can see why, or how obvious this is, that electromotive force, EMF, is really voltage. Because what makes electrons move in a circuit? Voltage. Hook up a battery, make the electrons go out of the page in the wire, or move the wire up. It'll make the electrons go out of the page. So EMF, electromotive force, from your left-hand rule, your force rule, absolutely gives the same result as voltage. EMF is really voltage, right? So this is the motor force. So when I say here in the writing, the motor force on them, i.e. EMF, right? Electromotive force, which is the same thing as voltage. I probably have another page dedicated to this because I feel like I'm going off script a little bit. So I feel like maybe this page might be a good one to stay on for a little bit. So you can analyze and visualize things. A combination of the previous two pages maybe would be good, but this one and the previous one, but and it certainly shows the left-hand rule. I do like that we analyze the actual fields as well, though. So you might want to, there's that hand rule close up, by the way. E flow, north, palm facing, right? So make sure to be able to analyze the fields as well. The idea of the north-south direction. Okay, we're going to make the same one so that we oppose the motion. So by same one, I mean that this would be a north-south direction as well, right? Yeah. I hear a microphone. Is there a question? All right. So the result we're talking about here is that EMF, electromotive force, aka voltage, right? I've already analyzed and justified that. We could look at what would create the most electromotive force. Clearly, if you have a stronger magnet, you're going to get more force. Clearly, if you're moving the charges is important. If moving them is important, then more motion is going to give you more electromotive force. And the length of the wire that's in there, so you're picturing a force on each of these electrons, and the length in which you're exposed to forces is going to basically add up to the total amount of force. So we're going to say length is going to be a factor as well. And so by our usual right? Our usual, oh, this is the magnetic field we know is this, right? And so on. So we know all these relationships here. And so we could say, oh, well, we know that the proportionality, it gives you the same kind of equation as before. Where am I going here? My screen is freezing on me and I'm having trouble clicking. So I guess what I was going for here is the force, right? It's going to be proportional to the B and the V and the L. Does that look familiar? Right? That's that VBL or ILB sine theta business, right? ILB sine theta, right? So you got your length and you've got the current is to do with the velocity part, and you know that's really that same formula as before. So I don't think I really need this page, to be honest. We've already done it, and we've already done the units, I think, in the past as well, right? So here's the equation though: proportionality constant in the B and the V and the L. I think we've already done this. Have we already done this or not? Maybe not. So the magnetic field intensity is weird. The B value is newtons per amp meter, and that's why I showed this little formula here from before, newtons per amp meter. So just a quick unit analysis here, just for appreciating that this really is voltage, right? We got newtons per amp meter, we got velocities meters per second, we got length as meters. So cancel out meters, combine it, say, oh, Newton meters, you know, that's Newton meters is really work done, right? So that's energy. So I should have said here delta E, right? That's work done, delta E. And then the seconds canceled out, and we're left with charge in the bottom. Really, we get that this thing is joules per coulomb, which is exactly what we've defined voltage as in the past. So what I'm hoping you see this as is this is a unit analysis justification or confirmation that EMF, electromotive force, from the left-hand rule business, like, oh, there's a push on the electrons. I gotta get my screen back in control here again. Yeah, there we go. This, you know, the whole push on electrons thing really is actually voltage, right? So the push on the electrons is joules per coulomb, which is voltage. So it's just trying to connect this stuff all together, right? Here's a neat result for you. This is superconductor magnetic levitation. So I'll just show it to you at first. Got two different videos of it. One is just going to show levitation itself. So what's happening in here is the current that's induced. One of these is, snap, what happened? Did I do that or did it do that? Looked like it was going to show. No more off snaps. All right, so pause for a second. So this is a superconductor, and that's a magnet. That's one of those films that shows magnetic fields. It doesn't really matter, but they're going to put liquid nitrogen in here. And they're going to reduce the temperature of this conductor here to the point where it becomes a superconductor, which means that the electrons can flow with no resistance. That's what a superconductor is. So when they get the magnet here, and if a north is coming in, then we know electrons are going to flow to make a north to oppose it. Those electrons are going to flow forever, right? As long as this thing remains a superconductor. And so the thing will actually be suspended just because of that. So right there, it's actually floating there because there's a north coming in towards the magnet, which induces current to make a north that opposes it. And so the north is balancing gravity and it opposes it. Also, if you try and push it sideways, then that's going to induce like a new north over here, which is going to make new magnetic fields and current here to oppose it. So it actually gets locked in place side to side as well in this case, because a north going over would make a new north in this region, and so it's going to oppose it, right? It's going to oppose any change. So that thing is locked in place over that. But notice you can spin it, because spinning it doesn't create a new magnetic field anywhere. There's already however this thing is arranged. I'm guessing it's like a north-south, like I was trying to draw on the screen, I can't, but there's a north down and a south up, right? So spinning doesn't change that. And so it can actually spin, no problem. It's just that trying to move it left or right is going to create a north. Instead of being focused here, it's going to be a north that's focused over here. And so electrons are going to flow to create a magnetic field to oppose that change. Okay, but it can spin, no problem, because that doesn't make any new magnetic fields. So he forces it over, you can force it over there if you want, but then it gets locked in place by the magnetic fields created by the current. So it's actually current just zipping around in here like this, So electrons are actually flowing like this, let's say, to make a north up to be able to oppose the north that was trying to come in. So the idea of it being locked in place, excuse me, is shown even more in this video here, which, darn it, looks like I'm going to have to undo my, I don't have a link for that one. I probably could just Google it quick enough, but quantum levitation. So it's basically the same thing, but they design it in a fancy way so that it's pretty neat. Quantum levitation. Oh, I undid my keyboard. Bear with me for a second here. Quantum levitation, superconductor, blah blah blah. Here we go. And we can analyze these as we look at the video. In a minute. There we go. Moving on.
We have quantum locking. The superconductor is locked in space, and it stays wherever I put it.
So this time, these are the magnets, and that's the superconductor. But it doesn't matter which one's which. Obviously, you still have a magnet in the region of a conductor, and so on. So it's locked in place, and you can tell this is a rectangle shape, and this is a circle. And so if you try and move it to a new spot, and even if you try to rotate it, that's going to change what kind of magnetic field. I don't think that one can rotate.
This is quantum trapping.
Amazing.
As long as it's
so it's superconducting. It's frozen with liquid nitrogen.
Upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnet.
And that's because current can flow in here to make a magnetic field that opposes. It can't go away because that would be a reduction in the magnetic field. So electrons are going to flow to oppose that. It can't go to the left or the right because that'll create new magnetic fields. So the electrons are going to flow to oppose that. It gets locked in place. They call it quantum locking, but really it's just electromagnetic induction.
Dimensions, right?
Yeah, exactly.
So,
and you see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
I'm a little bit surprised it can't rotate on that one, but I'd have to look into the details of that part.
So
but the next part
the X and Y
is even better.
Yeah.
Let me go to
just
this part here. So they actually have a track with a bunch of magnets all lined up, and then a superconductor. And basically, it's all north-south, so it can be in any position along this track, and it's still just north-south in the same orientation relative to that disk. And so it can actually go flying along. Isn't that amazing?
It's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So you could tilt it as an angle, and it would still fly around.
Like this, and it will just go around like this. Because I go and put it at different height, and then like this.
If I had an infinite science budget, I would own one of these, and I'd have to buy liquid nitrogen. Obviously, it's pretty pricey to set up something like this, but very worth seeing. So if you're still trying to make the hovering skateboard from Back to the Future, this is about as close as we're going to get. You'd have to have magnets all along the road, and his surfboard would have to have a superconductor, and it's not surfboard, a skateboard, but have to have a superconductor in the bottom of it that is kept at minus 273 degrees, and he'd be able to float along on a skateboard. He wouldn't, however, be able to do kick flips and things like that because it would be locked in place. But this is probably as close as we could possibly get with science to showing or making that happen, like it was in the movie. So just one more little bit. So the good news is we only have one lesson going on today, so it's only be one set of homework. But this last couple slides here will possibly save an electric motor from dying a melting, hot, burning death in your lifetime. So if you're ever using like a blender in the kitchen, or you're using a motor that's powering a table saw, or any kind of situation like that, a drill, even electric drill, if the motor jams, it's important to stop applying the electricity to it, okay? Because electric motors, we know, are just a coil of wire. So there's very little resistance, right? So why, when electricity is connected, doesn't electricity flow too much and cause a short circuit? The answer is that the spinning of the coils, right? And of course, then the spinning of the electrons in it. So we are going back to this slide here. We're talking about the wire moving up is actually electron flow, right? And so magnetic fields are forces are induced in here that oppose that motion. We're thinking about that in terms of a motor. So the spinning of the coil, that's actually electrons moving in a magnetic field. We know by Lenz's law, we can just say very simply that that's going to cause there to be a magnetic field that opposes the motion, right? And so what that does is it causes an opposition to the actual flow of electrons. We call that force backwards on the electrons back EMF. It's called back voltage. So an electric motor will spin, of course, when electricity is applied, but it'll get spinning to the point where it won't spin faster because the electrons are actually slowed down in the coil by the voltage backwards on them. So you apply 12 volts to it. Eventually, it spins to the point where there's 12 volts applied backwards, and then no current flows for a bit. Then, of course, with friction, it'll start to slow down, which means the back voltage drops, which means now there's some net voltage forward. And so it starts to spin again, right? It starts to get some more push on it to spin, I should say. It was always spinning. But as it starts to slow down, some more current will flow to speed it up again. And then it'll reach the point where the back voltage balances the applied voltage out. So when an electric motor is spinning freely, very little electricity is going through it. That's why fans and things that run, motors that run, they're actually really efficient because not much electricity goes. So this page describes that, I believe, that we've got a push. Lenz's law says that the push that creates it will oppose the motion. And so it's basically applying a back voltage. So if we have a 10 volt applied here, we're going to end up with 10 volts applied backwards. And I've got it listed as like 9 volts applied backwards, leaving like 1 volt of energy to actually, or 1 volt to push on the electrons and the amount of current that would flow, that's just basically going to go to work done continually, right? But when you first turn an electric motor on, it draws a ton of energy because it's just a big old coil of wire, right? It's just a big coil of wire. If I go back to way up here, we saw motors are really just a coil of wire. If you apply a voltage to that, there's nothing stopping the electrons from flowing. There's zero resistance. It technically is a dead short at first. So you get a huge amount of current at first, but very, very quickly, ideally, very quickly, the thing starts to move and the motion slows that current down lickety split, right? Slows it down nice and fast. So it doesn't overheat. So they actually have, back in the day with fuse panels, they had slow blow fuses that were designed to allow extra current to flow a little bit for a little while, as long as it didn't flow for too long. And they were good for circuits where you had like a water pump kicking on, because a water pump, the electric motor kicks on, and at first you got a ton of current flowing until finally it starts to go and turn enough that it gets back voltage on it to slow the current down. If you've ever turned on a table saw in the garage, you probably have noticed the lights dim a little bit at first when you first turn it on. That's not because it's such a powerful table saw. It's actually because so much current flows through the coils of the motor until it starts to turn. If you don't do this, because obviously you don't want to cut your hand off, but if you use like a drill or something to like spin the circular blade on the table saw manually, got it spinning in advance and then turned it on, right, and it was going the right direction, the lights wouldn't dim because it would already be turning, it would already spinning, it would already have back voltage. So if the motor jams, there's going to be no spin, which means there's going to be no back voltage, which means that there's going to be nothing to stop the current from flowing, which means it's a short circuit, which means the motor will burn out. Okay. So unless that motor happens to be liquid cooled, I have a short story about that one. When I first moved into this house here, someone said, "Oh, the lights out in the bathroom downstairs." So I went and checked the breaker, and sure enough, there was one that was blown. And I was like, hopefully it's not for a reason. So I flipped it on, and as I'm walking away, I hear a click. The breaker goes off again. I'm like, So of course, being an idiot, I flipped it again and hoping it would be something different that time. And it of course broke again, right? The circuit broke again. Well, what was going on was the light in the bathroom was on the same circuit as the sewage ejection pump, which is an electric motor attached to like an impeller that, you know, causes the liquid inside of the sewage ejection pump to go up the pipes out to the septic bed. And so it was jammed because someone at some point had either dropped by accident into the thing or flushed down the toilet or whatever, a faucet. Like, you know, at a garden hose, you got the handle and the spout. So it's the spout portion, the threaded end on one end and the garden hose end on the other. Big plastic one of those was down inside the sewage ejection pump. So very luckily, my parents were here at the time helping us move, and my dad has no gag reflex. He is not grossed out by anything. So I was there helping, whatever else, but we took the top off of it, and of course, like choking smell instantly. I'm gagging. My dad's like, yeah, whatever, it's fine. Sticks his hand down inside the impeller of the pump, reaches around in. He's like, oh, there's something caught in here. He's got the liquid, I'm just going to call it, from the sewage ejection pump all over his hand. Anyways, no gloves. He's just reaching around there, and finally he manages to like turn it to the right angle and take it out. And yeah, we threw that in the garbage, put the lid back on. The sewage ejection pump is still running to this day. So what saved me? I didn't turn the switch on too many times, right? The circuit breaker blew to stop current from flowing. But if it didn't blow, obviously the coils and the wire would have gotten nice and hot and started cooking the liquid inside of the pump. But it didn't flow for very long, so any of the heat got you know, dissipated by the absorbed by the liquids, and so it didn't burn out. So yeah, if you're in the kitchen though, using like a mixmaster, blender, whatever, and it's going really slow because there's not much liquids in the mixture yet, and so on in the kitchen, and the motor's turning really slow, and you can hear it struggling, turn the motor to a higher setting so it can actually get some spin, so it can get some back voltage and stop the motor from getting too hot. That is a real life saving, well, these blender saving tip based on the physics we just learned. Back voltage. So the textbook, it's actually in the 3U textbook. So online, you're going to see a file. Let me just go in here. Online, you're going to see a file for lesson 25. Yeah, lesson 25. You're going to see a file that says lesson 25. It's going to be this one here as a PDF, right? Lesson 25, electromagnetic induction, PDF, whatever. Then you're going to see also the lesson 25 homework answers, but you're also going to see lesson 25 3U text pages. That's just the text pages to do with electromagnetic induction and the questions to do with it. The grade 11 book does a much better job showing this than the grade 12 book. It really glosses over and I don't know, doesn't do a good job showing it. So I don't even want you to look at it. I just want you to use the grade 11 stuff. And apparently I was either a lot of material or I was really long-winded today. But yeah, the actual assigned work is very reasonable. Give you a chance to get caught up on things if you're a little behind in other areas. So tackle this stuff, get it done. There's homework solutions to help you, and then tackle other stuff. That assignment, of course, is due by the end of the day today as well. So don't forget about that. And oh, and I am available today at 1 o'clock. I'm going to log in at 1 o'clock today, but tomorrow I am not because I'm going to get a vaccine. So that's good news. Everybody's going to get it soon, but yeah, good stuff. So that is, so that's the stuff we're getting to soon. Spoiler alert. But yeah, there's the lesson I'm going to upload soon. I will stop rambling. I'm going to stop the recording and stay logged in for the next 5. And then again at 1 o'clock, I'll come in.